Good afternoon, everyone. Welcome back at the D&E event. This is the almost the final presentation of the day. Stuart Murlis from PicoTech is here on behalf of CNRood. I will shortly introduce him to you, and then it's up to Stuart to give his presentation. Arthur Hartsuiker and Paul Allen are here as moderators in the chat, so ask the questions in the chat. They will send it to Stuart or answer them themselves. At the end of the presentation, we will have some time left to answer a few questions. And last thing, you can set your screen to full screen by clicking on the arrows. Just enjoy the presentation of Stuart. Stuart, it's up to you. Good luck.
Oh, brilliant. Thank you very much. And presentation. Well, very warm welcome from not so sunny United Kingdom. My name is Stuart Murlis. I'm the FAE for PicoTech, and today we're going to talk about the challenges of debugging mixed signal designs. So, bear with me one moment while I get the slides set up. Apologies. Melvin, I can't seem to see the slides.
Stuart, I'm back again. You can click on the fifth icon, the little landscape. There it will be available.
Apologies, my fault. Gotcha. My fault. I'm not used to the webinar geek, so apologies for the short interim there. So, all right. So a little bit about PicoTech. It was founded in 1991, and currently we have 140 employees based out here. Our headquarters are here in the UK, and that's where a lot of our instruments are designed and manufactured here in the UK with a 21 million euro turnover. We also have offices in Tyler in Texas, in the United States or North America, and we also have regional offices in Shanghai and Tokyo. So, currently to date, we're the market leader in PC-based instruments. Okay, so what we do is we have three divisions to our business. We have oscilloscopes, real-time, high bandwidth, some RF products, and some data loggers. But today I want to talk to you really about the setting the scene about the challenges we face, with embedded systems. And so embedded systems frequently combining analog RF power electronics with complex digital hardware. So virtually every electronic device produced today has an embedded system. So there's a combination of both analog and digital elements, ranging from ordinary microcontroller based designs to high performance electronics, used to monitor and control the features in our cars, from radar systems that we drive today and the radar systems of tomorrow. So consequently, high reliability embedded systems are deployed in applications ranging from aircraft flight decks to power distribution networks. And of course, millions of low-cost Internet of Things household appliances and consumer devices are built around embedded systems. So taking it to embedded technology trends, designs are becoming much more sophisticated. So the measurement of waveform pulses and cycles is key to verification of these design processes. Processes are getting faster, signal processing from multiple sensors. So whether it's a MEMS device, we've got a combination of video and audio. And of course, advanced power management technologies are required to keep all these things working in synchronization and Internet of Things connectivity. Low-speed serial buses are not so slow anymore. And serial bus communications and wide digital input and outputs. So as designers, what debug and verification challenges do we face? So large pinout devices operating at high speed. We need to be able to look at those design verifications, the integration onto the PCB, and of course, signal integrity issues are everywhere. We need to be able to capture high-speed events and verify timing noise margins, intermittent and infrequent faults, the cause and effect correlation, deep dive, and of course, power integrity concerns too. Consequently, we need to do more with less. So, there's a continuated pressure for time to market, design integrity, proof through statistical analysis of measured results, and of course, equipment budgets are always under pressure, and restricted bench space. So I'm going to address some of these mixed signal challenges with my setup here, which is the 6000E PC-based oscilloscope, which is high performance, deep memory, has a combination of both analog channels and high resolution, flexible resolution, and of course USB hardware acceleration and support for HD and 4K UHD displays. So we also have the digital channels, 8 digital inputs, and we're going to use some of these today to look at a DAC output. Innovative ground clips designed for easy connections and ground leads and mini test hooks. So with the ability to adjust the hardware characteristics of the ATD, we can adjust our resolution, and this is a key factor when we're looking at mixed signal designs. With digital characterization, we need high sample rate, we need deep memory, and we also need a way of effectively using the measurement functionality within the software to achieve our measurement requirements. On the converse, with analog requirements on a mixed signal design, we need to be able to look at the smaller signals in higher resolution. And I'm going to start today by looking at how the architecture of the 6000 can be used to characterize a noisy clock, for example. So just excuse me now while I go to the software, and let me just click on share screen. Just bear with me. Could someone confirm they can see my screen, please? Okay. Right, so what you can see running here is a 20 kilohertz clock, which potentially has some asynchronous noise on it. So if I add a view in spectrum mode, you can see now I'm just going to inject 2 meg of noise onto my system. And just pull this down. As you can see there, we've got some asynchronous noise that is actually passing through our clock signal at 2 megs. I mean, I would need to characterize that by using flexible resolution. In other words, we can reconfigure the hardware, the ATD, and what we can do is adjust it to actually look at the noise that is superimposed, asynchronous noise that's on our clock. So if I now was to zoom into that noise, you'll notice there that in 8-bit mode, I can see there's something present, but if I now switch to true real flexible hardware resolution, I can actually see the synchronous noise. Now, to illustrate this further, I'm going to just compare 3 resolutions, and just bear with me. Okay, so what you can see there is if I switch, that's 8-bit, that's 10-bit, and this consequently is 12-bit. And just to switch through to back to 8-bit, you can see that I'm characterizing my noise on my clock signal. So now, just to show you the dynamic range of the instrument in terms of capability, I'm just going to switch through to my and I just going to switch through. And there you can see, as I switch through to 12 bits, you'll see my noise floor will significantly jump down, thus showing you the capabilities, looking for synchronous noise on a clock system. Just to go through. Right, so as you can see, in 8 bits, we can still successfully see our acquisition, but in 12 bits, we can actually see the asynchronous noise. And as illustrated, our dynamic range reduces the noise floor from, in 8-bit mode, from 50 dB to 60 dBs SFDR. So, also, one of the things when we're addressing mixed signal designs is we need to be able to look at our serial data in comparison to our timing. PAM3 software, for example, we have a software directional coupler, which will allow us full view of duplex traffic in both directions. So in other words, from the decode to the master, the slave, and the master traffic in graph and in table view. And using the filtering and search, we can look for timing and glitch violations within, within our acquired protocol. So another key factor when we're addressing mixed signal designs is the ability to use deep memory to our advantage. So here you can see a picture of Europe. As I fade in, we can see a picture of the UK using deep memory. And thirdly, when we can actually see a zoomed in picture of Pico HQ in the UK. So what is deep memory used for? Deep memory gives us the ability to acquire long continuous waveforms, capturing multiple events. It will also allow us to capture random glitches, and I'll illustrate in a minute the abilities of the deep memory capabilities in looking at mixed signal applications. So again, I'm going to share my screen. Right, so what I have here is a pulse output, okay, which is, it's running live. What I've done is I've simulated with interpreting and inserting a random glitch into my system. There you can see using
Stuart,
the AWG.
Your screen isn't shared right now. You only have
okay.
your presentation visible.
All right, apologies. Sorry for that. I did click on the button. One moment. Just let me come down again. It's my fault. I didn't click share. So, is that better?
Yes, there it is.
Yeah. Apologies. Yeah. Okay. Just to illustrate some of the characteristics of deep measure, what I have here is a pulse train which has got a random glitch in, and I've simulated it using an arbitrary waveform generator, and you'll see there that there is a random glitch. So the ability to capture a vast amount of data as quickly as possible is key to finding violations or glitches or errors. So I'm going to illustrate this. So here I've got a glitch, a random glitch. Now I could use persistence mode. Okay. And there we can see there is a glitch there. The disadvantage here is I can't see what happened before and after. Using deep memory to catch a glitch, what I can do now is create a mask, and then we'll use a feature known as rapid trigger to capture 1,000 waveforms as quickly as possible. So I'm just going to create a mask. Okay. I'm going to use a mode called rapid, and then we're going to capture 1,000 waveforms as quickly as possible. You'll notice now that I have actually caught 1,000 waveforms. Okay. In rapid mode, what we can do is we can guarantee the trigger rearm time, the dead time between triggers. It's guaranteed at less than a microsecond. Okay, so now I can use my filter search there to show my mask failures. And what you can see here, it's a repeating pattern. If I now look at this, I can now clear my mask. And there I can now characterize my glitch. I can also see what happened prior to the event or post-event. This could be sent on to a client. We could save the data. It's available. Another advantage of deep memory capabilities when looking at mixed signal designs. So stop sharing is there. Thank you. So next, we're going to talk about deep measure. Deep measure gives us a lot of capabilities. What we can do is one waveform and characterize millions of measurements. So design integrity through statistical analysis. So what we can do is, using our deep memory, we can then validate our design integrity by looking at deep measure. We can look at deep memory trend analysis. So what I have there is a varying waveform, and I can actually look at the frequency components using advanced mathematics to characterize and make a frequency trend of my signal characteristics. One of the things that is always is that we have segmented buffer in a lot of instruments. The memory store, the record length is 1 buffer. We use memory segmentation, and we can store up to 10,000 waveforms of buffers, allowing us detailed statistical analysis. With the 6000 series, what we can do is you can use a deep memory combined with high sampling rate, and what we do is we use a hardware acceleration. In other words, when the acquisition is acquired, it goes straight from FPGA into memory, okay, and therefore allowing fast and effective transfer of the data onto the screen, into the software. So we can segment the memories, and as I illustrated previously, we can actually scroll through our memory segments, our memory buffers, allowing us time to achieve our glitch characterization or looking at our mixed signal designs. So as I was illustrating earlier, we used rapid block mode to characterize and capture a random glitch. So you can create your own mask and you can search on violations. And of course, all this is very much time stamped. This is all, this is all very good for time stamping. So we can catch in rapid block mode, we can capture up to our screen waveform update rate is up to 300 waveforms per second. So moving on to the next example, I'm just going to talk a little bit about deep memory and deep measure. So deep measure gives us the ability to look at various features, the ability to characterize a signal and look at cycle time, frequency, low and high pulse width, duty cycle, rise and fall times, over and undershoot measurements, max and min voltages here. So it's going to bring up my share screen. And here we go. Share. Right, so what we can see there is, to describe what you're seeing on the screen there, I've got a DAC output, okay, on multiple channels from my digital element, and I'm characterizing D0. You'll notice that if I move my time rulers, you'll see that they're characterized. And what we can do is get statistical analysis of our D1, our DAC output on 0.1. Okay, what I can do is actually look through the cycle time, the frequency, the low and high pulse width, the duty cycle, fall time, undershoot and overshoot, and max and min voltage. So what we can do is we can characterize and create a statistical analysis of all our data on the screen with specific information on one pulse, for example, and characterize that with regard to frequency, high and pulse width. Another key benefit of having deep memory. So we use deep measure to actually look at statistical analysis of our waveforms throughout a given cycle. So just want to go back to segmented. Just want to go back to deep measure. So just to illustrate, so we can capture up to one waveform with millions of measurements. This allows us to characterize as many different segments of our acquisition as possible. So I'm now going to open the floor to any questions, and I hope that's been a good introduction to mixed signal designs and debugging by Pico. So thank you very much for listening, and if there's any questions, I'd be happy to open up the the floor for conversation. Thank you very much.
Thank you, Stuart. Thanks for your presentation. Let me have a look if there are any questions. Right now, there aren't any questions. So for the audience, if you have any questions left, send them in right now in the public chat so that Stuart can answer them. But we will wait a few seconds before we get any questions. But before we answer the questions, let me mention that we have one presentation left this day. At 2:30, we have the presentation of Erik Kroon from Nokia, and he will give a presentation about mobile edge computing, when and where to use it. So you can still register for this presentation. We start in about 23 minutes with the presentation, and I see the first question coming in, Stuart. So if you're ready. Okay. The presentation from Tom is, what is the price level of these scopes?
Right, okay. So depending, we have 4 8-channel versions, okay, in terms of the... It depends on your requirements, but the one I've illustrated today is the 6000E, which has been specifically designed to work with mixed signal designers and embedded systems. So I'll get you the price in euros. One moment. Okay, so depending on whether you want the 8 channels or 4 channels, what I'll do, if it's okay with you, to share my screen. It's just easier to show you the numbers that way. Yeah. So.
Yeah, no problem.
Yeah, okay. I'm just going to switch to euros, not this UK. Okay. All right, there you go. So we have a combination of either 300 or 500 meg, okay, or you can have the flexible resolution version, which I showed earlier, and you can have 2 MSO pods. So it ranges from 8,000 euros on 4 channels, or if you want the fixed resolution, it's 6,000 euros. So there's a combination. Please do have a look on the website. We'll speak to Arthur at CNRood, and we'll be happy to assist in any way we can. So thank you very much.
Okay, thank you, Stuart. I don't see any questions coming in for now. So yeah, let's end this presentation. Of course, if there are any questions left, just send them in, and Stuart can even answer them. For the visitors, tomorrow you will receive an email with the link to the replay of this webinar, and we will share it on our website as well. Yeah, for now, thanks for watching, and I hope to see you back at the last presentation of this event. Have a good day.
Thanks, Melvin. Thank you.